yesterday. So, are you ready to give me an explanation that how we can relate the molar absorption coefficient with the specific absorption coefficient? Do you want me to give again a short summary of what we did yesterday?
Yes, sir.
Okay. So we actually discussed something about the laws of absorption and how absorption actually grew from making everybody understand that the amount of light absorbed by the absorbing material is proportional to the thickness of the absorbing material, as we have seen in this slide. So as the thickness increases, we have seen that how the extent of absorption also increases, and then we arrived at a relation that that was relating the amount of transmitted light with thickness, and as the amount of transmitted light is going to go on decreasing because the absorption is increasing with increasing thickness, we arrived at this relation, which stands for a negative slope. And then we tried to simplify the relation and arrived at a relation which tells you that that the amount of light absorbed is directly proportional to the thickness of the absorbing material. In the similar manner, now when we talk about increase in the absorption in relation with the thickness of the absorbing material, what exactly is absorbing inside the absorbing material are molecules or atoms. And when we are talking about increase in the thickness, what we are actually doing is that we are increasing the number of molecules in the path of light. And hence it is also referred to as path length very routinely, the thickness. And putting this logic, there was another law that was put forth that is called as Beer's law, and which said that the amount of light absorbed by the absorbing material is directly proportional to its concentration. So instead of increasing thickness, what if we increase the number of molecules which are going to interact with light? And with this concept, the second law came into existence. And in the similar manner that we derived the relation for direct proportionality of thickness with extent of absorption, in a similar manner, we can arrive at another relation wherein we can state that the amount of light absorbed by the absorbing material is directly proportional to concentration also. And hence we combined the two laws together and arrived at a combined relation where we can say that the amount of light absorbed is directly proportional to thickness as well as concentration. And we can have a proportionality constant there, which is also called as the absorption coefficient or the extinction coefficient. And when we put all these two laws together and give a combined statement, then this law is also called as Beer-Lambert law or Buger-Beer law, or simply Beer's law, for understanding the relation between absorption and concentration as well as path length. So when we arrive at this relation, then there is another interesting facet that we actually explored, that depending upon what are the units of concentration and path length, as we now know that there is no unit for absorption, we can arrive at a relation which can describe more efficiently the absorption coefficient. And the units for absorption coefficient, when we solved it for concentration expressed in terms of moles per liter, then the units for absorption coefficient become liter per mole per centimeter, or it also can be written like it is when the concentration is represented in terms of grams per liter, then we can write it like liter per gram per centimeter. Now, depending upon which, what you can say, how we are expressing the concentration, we actually arrived at an understanding that we can have two ways of representing absorption coefficient. It can be either represented as molar absorption coefficient, or it can be represented as specific absorption coefficient. So we stop here, and I put forth a question for you all, that can we arrive at a relation between molar absorption coefficient and specific absorption coefficient, as now we know that what are the units for molar absorption coefficient and what are the units for specific absorption coefficient. So can anybody relate these two things together, molar and specific absorption coefficient? Or did you try to actually derive the relation? Yes? Anyone? This is where we stopped yesterday, right? So
Yes,
is this much fine with you? That means the relation for, or the units for molar absorption coefficient are these, and the units for specific absorption coefficient are these. So did you try to find out what could be the relation between the two? How many of you tried actually to find out?
yes, sir.
You tried. Okay, what's your name?
Pooja.
Okay, Pooja. So can you tell me what's the relation between the molar absorption coefficient and specific absorption coefficient?
Sir, I didn't find the answer,
Okay.
but I thought if I find the relation between mole and the gram,
Mm-hmm.
then we can correlate it with that
Yes, very correct.
specific
So
specific coefficient. And
did you find any relation between moles and grams?
not exactly, sir, because it is everywhere showing that the number of grams in 1 mole is the atomic mass number only.
Atomic mass number. Are you sure?
Not atomic mass, not number.
Okay.
matlab, it was given that if 1 mole of magnesium consists 23 point something gram, so मतलब atomic mass ही बता रहा था, so मैं किसी conclusion पे नहीं पहुंच पाई, so I was confused.
First of all, let me clarify this. This is not atomic mass that you're talking about. You're talking about atomic weight.
Weight.
So there is a difference between mass and weight.
Yes,
I
sir,
hope
yes.
that you know this, that there is a difference
Yes, sir.
between the two, right? Okay. So it's better to call it as atomic weight.
Atomic weight.
Right. So did you try to find out what's the relation between molecular weight and moles? Let me give you an example. Do you know this quantity? It's called as molarity.
Yes, sir.
And yes. And the relation for molarity is moles of solute upon volume in liters. So if I want to represent it in simple terms, it is weight in grams upon divided by molecular weight. That will give you the number of moles. So now can you arrive at any relationship? Or to make it even further easy for you, molarity is nothing but grams per liter upon molecular weight. So can you arrive at some relationship now here? pretty simple now, very, very easy. I have given you I've opened all the cards for you. If I say molarity is grams per liter upon molecular weight, what's your understanding now? Grams per liter upon molecular weight is molarity, or moles per liter, in other words. So can you solve this relation now? Anyone? At least give it a try. Okay. Maybe I will help you. Now, molarity, as I told you, it's gram per liter upon molecular weight. Looks similar to something?
Yes, sir.
Right. So, can you now relate the two things together? Yes. Any relation? Can I write it like this? See, as is written over here, the molar absorption coefficient is equal to, is given in terms of molarity, molarity inverse. Moles per liter is nothing but molarity. Okay, so it's molarity inverse, centimeter inverse. So instead of writing molarity inverse, can I not write it, because molarity is gram per liter upon molecular weight, can I not write it like gram per liter upon molecular weight whole inverse? Can I write it like this? Instead of writing molarity inverse, I can write it like gram per liter upon molecular weight entire inverse, whole inverse, right? Times
Yes, sir.
centimeter. Now solve this. It's pretty easy now. It becomes liter per gram times molecular weight times a centimeter inverse. Now, if I rearrange this, then I will get to liter per gram per centimeter. Is it similar to something?
Yes, sir.
Yes, sir.
Similar to what?
Specific absorption coefficient.
Yes.
unit.
So can I not replace this entire term liter per gram per centimeter with specific absorption coefficient?
Yes, sir.
Yes, sir.
So if I replace it with that, then I arrive at this relation that molar absorption coefficient is equal to specific absorption coefficient times molecular weight. So now if the compound is known to me, or its molecular weight is known to me, and if I know its specific absorption coefficient, then can I not calculate molar absorption coefficient?
Yes, sir.
Right. Now there is one more thing that you need to pay attention to. Now I hope that this much is fine, that molar absorption coefficient is equal to specific absorption coefficient times molecular weight of that particular compound. There's one more thing that we need to pay attention to here. And that is the most important question. Why are we paying so much of attention on absorption coefficient, understanding absorption coefficient? How many of you have heard this term for the first time, absorption coefficient? I bet that you must have learned about absorption coefficient previously, right?
Yes, sir.
But do you know what's the use of it? Why I'm paying so much of attention on absorption coefficient? The reason is this. Now consider this, okay? NADH, you know this compound? NADH, have you heard about this?
Yes, sir.
Yes, sir.
Right.
Yes.
This very common, you can say, a coenzyme that is used by dehydrogenases. And this is nicotinamide adenine dinucleotide, the reduced form of it. Okay, so NADH absorbs at 340 nanometers. Now, this is the wavelength at which NADH loves to absorb, likes to absorb. Okay, and its molar extinction or absorption coefficient at 340 nanometer is 6.3 into 10 raised to 3 liter per mole per centimeter. Okay, when I say this, what do you understand? The first line. What do you understand? When I say that NADH absorbs at 340 and its molar absorption coefficient is 6.3 into 10 raised to 3 liter per mole per centimeter. What's your understanding now? Let's get back to the slide where we actually established our understanding of absorption coefficient. If I rearrange this, let me give you another perspective of understanding it. If I rearrange this relation, which is the Beer's law, that is capital A is equal to small a, small b, and capital C. If I rearrange this equation and solve it for small a, then can I not write it like small a is equal to capital A upon small b times capital C? Can I not write it like this?
Yes, sir.
I can write it, right? So now, in other words, can I say this, that absorption coefficient is nothing but absorbance per unit path length and concentration? Yes, can I say this?
Yes, sir.
Yes, sir.
What I'm trying to put forth is something like, if path length is 1 centimeter, which is most of the times it is, okay, path length is 1 centimeter, so this value becomes 1. So I can write it like absorption coefficient A is equal to capital A, that is absorbance, upon B. The B path length is 1 centimeter, so I can write it like 1. And concentration, if I'm representing it in terms of moles per liter, if the concentration is 1 molar, so it will become 1 again, right? So can I write it like this? Molar absorption coefficient is nothing but absorbance of that particular compound per unit path length, that is 1 centimeter path length and 1 molar concentration. So it is nothing but absorbance, right? Representing absorbance in standard terms. Are you getting my point?
Yes,
Yes,
sir.
sir.
Okay. Now I'm again putting up this situation in front of you. And now I ask you this question again, that if I say that NADH absorbs at 340 nanometers and its molar absorption coefficient is 6.3 into 10 raised to 3 liter per mole per centimeter, what do you understand? Yes? Am I asking a difficult question? What is molar absorption coefficient? We have just found out. What is molar absorption coefficient? It is nothing but absorbance when path length is 1 centimeter and concentration is 1 molar. Can I say this?
Yes, sir.
Yes, sir.
Right. So if I say that NADH has a molar absorption coefficient of 6.3 into 10 raised to 3, then what do you understand by this term?
That its absorbance at 1 molar concentration and 1 centimeter path length.
Is
Absorbance.
what? What is the absorbance?
6.3 into 10 to the power 3.
Correct. So it's nothing but when I dissolve 1 molar or 1 mole per liter of NaDH, if I prepare this solution of NaDH 1 mole per liter and check its absorbance at 340 nanometers, which is its what you can say wavelength at which NaDH absorbs maximally, then at 1 mole per liter concentration of NaDH, it will give me an absorbance, capital A will be equal to now, absorbance will be equal to 6.3 into 10 raised to 3. Is this much fine?
Yes, sir.
Yes, sir.
Right? So now absorbance equates absorption coefficient when path length is 1 centimeter, which is most of the times it is. So if I am not describing path length, it is 1 centimeter. And if the concentration is 1 mole per liter, then absorption coefficient AM is nothing but absorbance. I hope that the point is clear, right? Now, if this is understood, can you solve this for me? If this much is fine, should I go ahead? You have this value with you, right?
Yes, sir.
Now, can you solve this question? That if a solution of NaDH shows an absorbance of 0.63, what is the concentration of NaDH in solution? Can you find this out? Now you know this relation, right? Capital A is equal to small a, small b, and capital C. Now in this question, absorbance value is given, right? Absorbance value is given, and that absorbance value is right. What is the absorbance value here?
0.63.
Yes. So can I not write it like 0.63 here? Correct?
Yes.
Yes, sir.
Now, small a value is also given, that is molar absorption coefficient, which is 6.3 into 10 raised to 3. Fine. Path length is 1 centimeter because it hasn't been talked about here, 1 centimeter. And concentration we don't know. So we need to solve this for concentration. Can you do that?
Yes, sir.
Right. So solve it and let me know what's the concentration. So what point I'm trying to make here is, now you can solve this, right? I hope that you can solve this. And we can arrive at the value of concentration. So the point I'm trying to make here is that if we know the absorption coefficient of any compound, then we can determine its concentration just by checking its absorbance. Can I not find out its concentration?
Yes, sir.
Yes,
Right?
sir.
So does it make absorption coefficient to be a very powerful tool of finding out concentration just by checking absorbance values?
Yes, sir.
Right? So if you know absorption coefficient of any compound, and if I give you an unknown solution of that compound, what you will do then? Yes?
We will find out the absorbance and then
Right.
calculate it.
Yes, then you can calculate the concentration. The reverse is also true. If you know the concentration of any unknown compound, can you calculate the absorption coefficient?
Yes, sir.
Right, you can calculate the absorption coefficient. And once you know the absorption coefficient, it becomes very easy for you to determine the concentration of any unknown solution of that particular compound whose absorption coefficient is known to you. So it's a powerful, what you can say, quantity, correct? And hence absorption coefficient understanding has to be clear in your mind. I hope that I have clarified what is absorption coefficient and how powerful that unit can be for you, right?
Yes, sir.
Is this much okay? Should we move ahead from here?
Yes, sir.
Right. Okay. Now till this point, let me ask you this question. How many of you have studied absorption coefficient in your graduations? I bet everyone must have studied, right? But how many of you knew this is the utility of absorption coefficient? Yes? Nobody, right? So is it not surprising that we learned about this quantity in our graduate studies, but we weren't aware that it can be used in this way? This is an important thing to remember, correct? So I hope that I have done justice for making you understand that what is the importance of absorption coefficient in the absorption studies, right?
Yes, sir.
Okay, so let us move ahead now. We can do one more thing here, and then perhaps we can talk about something else. Okay, and so we talked about now absorption coefficient. We understood what's the importance, that if we know the absorption coefficient, we can calculate the concentration. Okay, and if we know the concentration, we can calculate the absorption coefficient value, right? So this is the second statement. So if we know the concentration and absorbance values, one can calculate the absorption coefficient, correct? Now, can you solve this for me if you have understood exactly what's the utility of absorption coefficient? Now, imagine that you don't know what's the concentration. Okay, so let me give you a situation here, that you have an unknown compound X with you. Okay, the compound is not known, but you know that the compound gives you good absorbance, or it absorbs well at a particular wavelength value. Okay, so now because the compound is unknown, its absorption coefficient is also unknown, and in a, in a matter of hurry of finding out absorption coefficient, you have dissolved that compound in some amount of, say, distilled water, and you forget, while doing this, you have forgotten to find out what was its concentration. So you don't know the concentration, you don't know the absorption coefficient. Can you still find out what is the absorption coefficient just by recording absorbances of this particular solution of compound X? Did you get the question? Is the question clear?
Yes, sir.
Okay, so can you find out absorption coefficient now for me? So I give you an unknown concentration solution of compound X. The compound X is unknown. The solution in which compound X has been dissolved, the concentration of compound X is also not known to you. And now the task is to find out absorption coefficient of this compound X. So can you find it out for me? Is the question clear enough?
Yes, sir. Yes, sir.
Okay. So can you answer? Yes. Do you want a hint so that it can help you answer the question quickly?
Yes, sir.
Okay, let me tell you that you have done this several times during your graduation practicals.
So we will plot a graph with the help of absorbance and find out the concentration, and then we'll use that concentration to find out absorption coefficient.
Okay, how will you plot the graph? In order to get to the graph, you will have to plot concentration on x-axis and absorbance on y-axis, right? You don't know the concentration. So what you will plot on x-axis? Yes? Is it a valid question to ask?
Yes, sir.
Yes, sir.
Right. Okay. So what you will plot on x-axis? Because you don't know the concentration. Yes?
Concentration of standard.
Concentration of standard. For that, you should know what compound X is, right? In order to prepare standard of compound X.
Yes.
So whatever amount of compound X I had with me, I dissolved it in water, and I forgot to find out or measure or weigh compound X before dissolving. So I have given you that solution of compound X now, of unknown concentration. And the compound X is also not known to me. So I cannot prepare standards of compound X. So what you will do then? Yes?
So we'll have to
Sir, we will,
identify X first.
But you have prepared the solution of it. So how will you go for identification now?
sir, we will prepare a range of samples.
How? But I have given you one solution of X, right? With that only you will have to deal. You cannot take extra X because I have dissolved everything. I have given the solution to you. Now you tell me how you will proceed. To prepare a range of standards, you should have a standard concentration known to you, correct?
Yes, sir.
Yes,
Yes,
sir.
sir.
So can you do that now? And don't forget the task. The task is to find out molar absorption coefficient, okay? Let me tell you, you all were mostly on the track. So you were quite close to find it out. But how can you do that? Yes?
So chemicals like chemicals have you can say specific absorbance, no? So by recording the absorbance, we can try to identify the range and the compound.
You know,
Like
can you
because
elaborate? I didn't understand it properly what you are trying to say. So can you just elaborate on what you are trying to say?
Yes, sir. I was saying that every compound has a specific range of absorbance, no? For what we are trying to find.
Range of absorbance means what?
So range of absorbance, like we are taking the readings, no?
Yes.
Like DNA absorbs at a specific wavelength.
Yes. So what?
So I'm trying to say that we can use that absorbance to identify that
Okay.
compound.
Are you trying to say this that because DNA absorbs at 260, anything that absorbs at 260 becomes DNA?
No, sir. I am not talking like it's specific. I'm just saying like we can try it.
Okay, then try it. So if I tell you that compound X absorbs at 340 nanometers, does that make compound X NADH? Yes.
So not specifically, but at least the range of compounds is narrowed, no?
There are a hell lot of compounds which absorb at 340.
Okay.
It's not only NADH that absorbs at 340, right?
Yes, sir.
So how can you narrow down the search? Okay, so you narrow down the search. Say, now you know that, say, 1000 compound absorbs at 340 nanometers. Does that help you? Do you know what compound X is now?
No, sir.
No. Is it helping you in any way what you are trying to say?
I'm not sure, sir.
It is not going to help you. It's actually going to complicate the matters even further for you. Yes, anybody? Okay, do you want me to solve it for you? I told you that you were on the right track, right? Again, use the same relation. Is this relation similar to this equation?
Yes.
Yes, sir.
And what does this equation stands for?
Slope.
Sorry. I can write it like y is equal to mx plus c, but c here doesn't work because there is no plus sign here in this equation. So obviously, if I plot absorbance on y-axis and concentration on x-axis, that's what you were trying to say, correct?
Yes, sir.
Then because path length is not going to change, path length you don't change the what you can say diameter of the cuvette while measuring. Do you do that?
No, sir.
No. So the
No,
path length is
sir.
going to remain constant, correct? So whatever you will get, the slope of the line will correspond to absorption coefficient, right?
Yes, sir.
But you solved this, right? The problem is, what are you going to plot as a concentration value? You may record absorbance, but what you will plot as concentration. So, can you not do this? Now, this is the graph for you. You are plotting the concentration, you are plotting the absorbance at different concentration values. But you don't know the exact concentration. So what you will do then? The slope is no doubt absorption coefficient. In order to find out the concentration, can I do this like this? Meaning, can I not do dilutions of the compound X? So I have the solution of X with me. Can I not do a range of dilutions?
Yes, sir.
Yes,
right?
sir.
And I plot those dilutions on x-axis. That's what you actually do, correct? You prepare a stock standard, and from that stock standard, you take out, say, 0.2, then 0.4, then 0.6, then 0.8, then 1, and you dilute it with water, correct? That's what you have done previously in your graduation practicals?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So you dilute the solution. So even if I give you a solution with X, you can very easily prepare dilutions of different concentrations of X, right? So I can prepare X by 2, I can prepare X by 4, I can prepare X by 6, and so on and so forth. Likewise, I can prepare X by 2, X by 3, X by 4, or X by 5. And with highest dilution, you will get the least absorbance. So X by 5 will be here. So in short, X by 5 will be here. X by 4 will be here. Is it making sense?
Yes, sir.
Yes,
Yes,
sir.
sir.
X by 3 is here. X by 2 is here. And X is here. And then you will take a zero concentration as well. That is called as a blank, right? And by preparing these ranges, I can prepare a standard curve, the straight line passing through origin, obeying this equation of straight line passing through origin, right? I can very easily find out the slope of the line, and the slope of the line will be nothing but the absorption coefficient. So now I have given you one more perspective of finding out absorption coefficient, even if you don't know the concentration of the solution, right? So can you find out absorption coefficient even if you don't know the concentration?
Yes, sir.
Yes, sir.
Yes. So this becomes a very important understanding of absorption coefficient. I bet that you never paid any attention during your practicals in understanding that what is it with the slope of the line, right? How many of you did this? See, you got, say, 2-3 different points. कोई भी एक point ले लो और straight line बना लो. ऐसे किया है पहले?
Yes, sir.
Right. So what you should do now, see, because this becomes an important thing. You cannot choose any point and just draw a straight line out of it, correct? You will have to choose judiciously the points which you are going to take on the line so that you get the slope of the line which is corresponding to absorption coefficient. I will come back to this point, but not now because we are still in the process of establishing our concept related to absorption coefficient and related to absorption spectrometry. But this at least makes a point clear in your mind that there is a value which is quite important, and that value is of absorption coefficient. It's nothing but the slope of the line which you are going to draw passing through origin when you prepare a standard curve. So I hope that this much is fine. Should I go ahead?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now comes the most important point. This is called as the concept of blank or reference that we actually use before we start doing these kind of absorbance recordings, right? So what is a blank? Can anybody tell me what is a blank? Yes?
It doesn't contain the sample of which we have to find out the absorbance.
Right. So can I say this, that blank contains everything except the compound of your interest?
Yes,
Yes, sir.
sir.
Yes,
Yes,
sir.
sir.
Okay. So now it contains all of it. It means all the reagents without the substance of your interest. So if I ask you this question, that this is my reaction. That means I'm interested in A. A is the compound of my interest, which is colorless. Okay. And if I want to do its absorbance studies, that means if I want to find its concentration or something apart from that, then I need to work out this chemical reaction. That means I need to mix A with B plus C. B plus C is the reagent which is going to give me a reaction happening with A, so that I get a compound D created, which is colored. Okay. So what is normally done in such kind of methods, these are the methods which are used during colorimetric estimations. If you are interested in A, you mix it with a coloring reagent, which is say B plus C here. After interaction of A with coloring reagent, you get D. So now this is your reaction. What will be your blank?
B plus C, sir.
B plus C.
Sure about it?
Yes, sir.
Yes, sir.
Okay. So instead of saying only B plus C, instead of adding A, I will add water there, and rest will be B plus C. This will make my blank, correct? Everybody agrees?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, good enough. Now, my reaction mix consists of, instead of water, it will contain A, then A will react with B plus C, you will get D, and against this blank, you will check what's the absorbance given by D. That is how you will proceed?
Yes, sir.
Yes. Okay. Now, there is a bit of a problem here. Imagine. What is in the reaction mix? Compare that there are 5 moles of A in the reaction mix, and there are 10 moles of B plus C. Okay. This will give you 5 moles of D plus 5 moles of B plus C remaining unreacted. Are you with me still?
Yes, sir.
Yes, sir. Yes, sir.
Okay, this much is fine. Are you okay with it? Yes?
Yes, sir.
Yes, sir.
Okay. Now there is a bit of a problem here. What will be your blank? Blank will be 10 moles of B plus C, because blank will not have any reaction happening in it.
Yes.
Okay, now imagine that the compound D, which you get after the reaction is done, absorbs at 540 nanometers. Okay, and 10 moles of B plus C in your blank, which is the entire amount of unreacted B plus C in your blank, gives you an OD at 540, which is equal to 0.1. Okay. While 5 moles of D that you get after 5 moles of A have reacted with 5 moles of B plus C, 5 moles of D that you get has an absorbance of 0.5. Okay, how many moles of B plus C are remaining now in your reaction mix?
5 moles.
5 moles. Now, if 10 moles of B plus C give you an absorbance of 0.1, 5 moles of B plus C will give you an absorbance of? Yes?
Yes, sir.
0.05, correct? So what will be the total absorbance in your reaction mix? 0.55?
Yes, sir.
Yes, sir.
And if you want to actually find out the absorbance only due to D now, you will have to minus the absorbance of the blank from this value.
Yes, sir.
And what's the absorbance of the blank?
Yes, sir.
0.05. 0.1, right?
0.1.
So what will be the resultant absorbance value? 0.45, correct?
Yes, sir.
But actually, what is the absorbance that is given by D?
0.5.
And what absorbance you will get after negating the blank?
0.45.
0.45.
So is this a good way of preparing blank?
No,
Yes.
sir.
No, sir.
So what's the problem? What is the problem you are sensing now?
The blank should be kept 0 always.
No, you will adjust blank 0. You adjust blank 0, correct? It gives you some absorbance, right? And you make it 0, correct?
Yes, sir.
Yes, sir.
Yes. So basically, when you make it 0, what you are actually doing is that you are adjusting this 0.1 to 0. So you are, in other way, you are actually negating blank from whatever absorbance that will be given by your reaction, right?
Yes, sir.
So instead of doing it mathematically in your book, what you do is that you adjust 0 in the instrument itself. So, but what's the problem? Are you sensing the problem here? What is the problem?
Yes, sir. The
What is the
quantity
problem?
taken in the blank is more.
Different, right? It is
Yes.
different. While when the reaction happens, some amount of B plus C is going to get consumed in the reaction, right? And that, can you control that? Yes. So are you preparing a good blank for you? Yes. Do you feel that this is a valid question to ask?
Yes, sir.
Yes,
Yes,
sir.
sir.
Right. Did you ever paid any bit of attention on understanding that how blank is prepared? Yes.
So we will not take 10 moles of B plus C. Instead, we will take lesser amount.
Okay. Take less. How much less you will take?
Maybe half of it.
So you will take only 5 moles of B plus C. You want to say this?
Yes, sir.
But you don't know how many moles of A is going to react with B plus C, because the sample that you are analyzing there, the concentration of A will be variant, right? So what if your sample contains 6 moles of A? If you take only 5 moles of B plus C, 1 mole of A will remain unreacted, right?
Yes.
So will it work for you?
No, sir.
No, sir.
So do you feel that this is how the blank should be prepared? Technically, it seems very simple, right? Add water instead of adding A, and add B plus C in the same concentration, correct? Like if you remember protein estimation by, say, Lowry's method, the amount of Follin-Lowry reagent or the amount of alkaline copper that you add, that amount remains same all throughout, correct? In blank as well as in other tubes, in the standard tubes as well. Yes or no?
Yes, sir.
It remains constant, correct? So it's almost 11:30 now. So what I will do is that I will leave you with this question. You will get one complete week time to answer this question. Okay. So do you take this challenge that you will be able to answer this question, or you will be able to find out answer for this question? And we'll discuss about this again in the next class.
Yes, sir, we will try.
Yes, sir.
Okay. Okay. So good that we will be discussing about this in our next class, and find out that whether you get to the answer or not. Okay. So let me stop here, and we will talk about the rest of the things in the next class. Okay, so if you have any doubts in the session that we